Hello, and welcome to Chapter 9 of Geology for Gilgit Community College. In this chapter, we're going to cover earthquakes and the Earth's interior. Right on the get-go, we see a lot of destruction in this first image. This is, most likely, I'm going to infer, a tsunami that is a direct result of an earthquake. We're going to go through a series of 6 images showing the potential catastrophe that can result from an earthquake. Here, we have a picture from 2010 Haiti earthquake showing a building collapse, the result of building collapse in the rubble that pertained from it, possible life loss given this earthquake. Here we have the 1989 Loma Prieta earthquake. Again, destruction of a building. Notice, I'm going to point this out here. This building's destroyed. Look down the line of the road. Those buildings weren't. Why were those buildings not destroyed, but this building was? Well, something we'll talk about. Here we have a double-decker highway collapse. Looks to be a older earthquake from the graininess of the photo. And again, some parts collapsed, some parts didn't. Why did this collapse? If we look in the background, in the upper left corner, a very tall white building, tower if you will, that appears to be standing not too far away from this earthquake. Why is that? We'll discuss. Here's a picture of the 1906 San Francisco earthquake, one of the largest earthquakes in recent North American history. Major destruction, great loss of life. Why did the 1906 earthquake have such a great loss of life, but modern earthquakes of lesser degree, but not much less, have far fewer life loss statistics? Again, we'll talk about that. And then here we can see a very interesting image of a earthquake and the actual movement of ground that occurs. Notice here, if we look closely at this orange grove, follow the trace of the lines of the trees, you'll see them offset a little bit. This is the actual ground strike-slip fault offsetting left to right these trees, and it did it in such a degree that the trees themselves may not have collapsed. Again, here we have in this little circle picture, a fence that again underwent a strike-slip faulting, moving 2.5 meters, almost 9-foot break of this fence. Also, keep in mind, the fence is still standing, it just was offset by the earthquake. Truly powerful stuff, really cool pictures. So, let's get some meat potatoes in on this chapter. What is an earthquake? Well, we're going to describe an earthquake, in this text, we're going to describe an earthquake as the vibration of Earth produced by the rapid release of energy. This energy release radiates in all directions from its source, which we'll call the focus, and the energy is released in the form of waves, which we'll call seismic waves. Certain sensitive instruments, called seismographs, around the world are capable of recording these focused seismic wave events. An earthquake can very often create what we call a fault, a large break in the crust along which there's been some sort of displacement. This was shown very well in that earlier picture of the orange groves and of the fence. Movements that produce earthquakes are usually associated with large faults. Most of the motion along faults can be explained by plate tectonic theory. Here we have a graphic with various terminology associated with earthquakes. Notice the focus or hypocenter of the earthquake is the point on the fault plane where the rupture actually happens. This is the break, if you will, the snap between these two tectonic plates that causes this energy to be released. Notice again, the energy is releasing in all directions, radiating out in all directions equally. We'll get into that a bit. The epicenter, a phrase you've probably heard when talk of earthquakes happens, is the point on the Earth's surface that is directly above the focus point. In this example here, we have a fault that shears in a certain direction. Here we have the left side shearing up, the right side shearing down, and the fault line on the surface is not where the epicenter is, because the fault itself has this orientation about it. That fault slides up in the fault scarp, that we call it, the part on the top of the soil, if you will, the part that you see that the faulting happens, will then move based on what's going on here. So in this case, the left block if you will, is going to rise and the right block is going to lower, causing an actual difference on the ground of, well, the left block rising and the right block lowering. So what is this energy release that we're talking about? This energy release relates to elastic rebound. It's the mechanism of earthquakes. So rocks, you have rocks on two sides of a fault, an existing fault. They slowly deform due to tectonic forces. Remember, we talked about tectonic forces in previous chapters, the moving of those large, gigantic plates on top of the lithosphere. So these rocks get pushed and shoved around, but they're rocks. They don't like to move that fast. They don't like to move at all. So what these rocks tend to do is they tend to bend and store elastic energy. So imagine taking a plastic ruler, if you will, put at the edge of the table, slowly bend down the ruler. That is a similar analogy, or I guess you could use a rubber band, or really anything that you can store elastic energy in. Here in this demonstration of elastic rebound, the book uses a limber stick. I don't know what that's supposed to be, but it does a good example of explaining this deformation. So you have, again, two tectonic plates. Let's picture large-scale tectonic plates for this example, and they're moving, but they're not moving together, so they are still bound with each other at some point, causing this elastic tension to form, right? It doesn't matter what direction they're moving relative to each other as long as they're not perfectly in sync. As time goes by, the plastic ruler bends and bends and bends and bends and bends. It keeps bending, keeps building this pressure. Eventually, as this pressure keeps building and building, the frictional resistance that's holding the rocks together is overcome. You have some sort of slippage at the weakest point of this rock intersection, which is where the focus happens, and vibrations, or an earthquake, occurs as the deformed rock springs back into its original shape. It snaps, reforms, and the energy released from the snap from this rock pushing back into place is the energy that is an earthquake. Earthquakes most often occur along existing faults, wherever the frictional forces on the fault surfaces are overcome. In the stick or rubber band or ruler, whatever you want to use as an example here, the breaking is the actual snapping of whatever had the elastic material on it. And then the vibration of the parts as they come back down to being calm is the energy released by the earthquake, the energy release of the earthquake itself. So the focus, the hypocenter, if you will, would be wherever the elastic material snapped. When it snapped is determinate based on the rocks involved and the force you put on it, right? Some rulers are easier to snap than other rulers, right? And then eventually, right, the ruler stops vibrating, comes back to stable form, essentially what it was originally, just in two pieces, in two separate locations, which is what happens. The rocks return to the original shape, but necessarily in new locations. After this major release of energy, you can have what are known as aftershocks, small quakes that follow a major quake. These quakes shift stress from the adjacent parts of the fault. Because even though the fault snapped at that one major location, there must still be other parts relative in this plate-on-plate structure that can release smaller amounts of energy as it goes. You can technically also have foreshocks, which are small quakes that precede the major earthquake by hours, days, maybe even years. Again, earthquakes happen because plates move. Plates move very, very, very slowly, as we talked about at the beginning chapters of this text, of this class. In general, you could consider there to be three major types of faults, places where plates meet. Divergent plate boundaries form what we call normal faults. Convergent plate boundaries form what we call reverse or thrust faults. And then transform plate boundaries form strike-slip faults. Small strike-slip faults, that's a tongue twister, are associated with divergent plate boundaries as well. Of all the faults that exist, the most studied, the most well-known, the one you've heard about, is the San Andreas Fault. This is a displacement that occurs along discrete segments of 100 to 200 kilometers long. It undergoes some fault creep, usually, which is a slow displacement of the faulting. and some segments regularly slip to produce small earthquakes. However, other segments store large amounts of elastic energy for hundreds and hundreds of years, rupturing into gigantic earthquakes. These earthquakes occur every 50 to 200 years. I said the San Andreas fault was the most studied fault. Well, who studies faults? Who studies earthquakes? Seismologists, or more particularly, seismology is the study of earthquakes and earthquake waves. This branch of science can date itself back almost 2,000 years to the Chinese were first studying this phenomenon. In general, seismologists use what are known as seismographs or seismometers. These are instruments that record seismic waves. The records of movement of Earth in relation to a stationary mass on rotating drum or magnetic tape. That's sort of an older description of seismographs. More recent models obviously use more advanced technology, but they all follow the same basic formula and structure. Here is an image and picture of a seismograph. Notice the seismographs tend to be in the left corner here, attached to some sort of bedrock, some sort of firm foundation that can accurately measure the movement of the Earth. This movement then goes up through a support beam connected to that bedrock onto a pivot and wire, and that suspended weight on top of this paper here rotates along with the bedrock, and this rotation is recorded, and then you can look back on it later to see what is actually going on within the Earth. And the important part here is this: a seismograph isn't just put on anything in particular. It's put on something, a bedrock of sorts, a firm foundation that accurately measures the movement of the surrounding Earth. Seismograms, or the charts made by seismographs, flow laterally along with time, and they also flow up and down along with intensity. So the larger a movement on the seismograph, the more the Earth was moving, and the wider the movement, the longer it took to move. So we can notice here in this fictionalized seismogram that we have a few bumps as well as a big mass of waves. We'll go into what these mean in a little bit, but the first bump we see, we have flat line earlier, right? The first bump we see is the first hint of a wave that showed up. Then later we have a larger wave, and then finally a big wave, the surface wave, which again, these red sections tell us minute to minutes. The surface waves, the waves that you would feel as a person, were not the first waves that actually were created as seismograph felt. There are waves, 5, 8, 9 minutes ahead of the surface wave. We'll get into all this stuff deeper as we progress throughout the chapter, of course. You notice on that seismogram we talked about different types of waves. Now let's dive into that. First we're going to talk about body waves. Body waves travel through the Earth's interior, starting from the hypocenter. If they travel primarily through the Earth's interior, we call them body waves. Within body waves, we have two primary types. The first one is the primary, or P waves. These have a push or pull, compress, expand motion that changes the volume of the intervening material. You can kind of picture this as grabbing a slinky, pulling it towards you, and releasing it. Primary P waves travel through solids, liquids, and gases. And generally, in any solid material, P waves travel about 1.7 times faster than the one we're about to talk about, the S wave. The secondary, or S wave, is a shaky motion at right angles to the direction of travel. This would be like taking the slinky, pulling it to the left or right, and then snapping it. This sort of wave only travels through solids, and as I just said, are slower in velocity than P waves. However, noteworthy here, S waves have a greater amplitude than P waves, and this is again something that we saw on that previous seismograph. Notice here that the first wave to arrive is the P wave. After an amount of time, an S wave arrives, and the S wave is larger. So we can take this information, we know how fast they're traveling based on that 1.7 velocity increase of P wave to S wave, we can figure out how fast they're traveling. We can determine, as we'll get to in a bit, determine where hypercenters are, where epicenters are, how strong waves are. All this can be determined off of P and S waves. Here are some images of the explanation I told you earlier with the slinkies, or in this case they describe S waves with a rope. You may have learned about these particular wave types in your high school physics class. I'm sure you went over this material. It's the basic same idea, just geophysicists, seismologists, geologists use different terms because they're fancy that way. In those seismographs, we saw there was a big wave at the end that was called a surface wave. Surface waves, as you would imagine, travel along the surface of the Earth, the outer layers of the Earth. They have a more complex motion of them, and the destruction earthquakes cause is a direct result of these surface waves. They have the greatest amplitudes, but the slowest velocity, and also the greatest periods, or the greatest amount of time between different crests of waves. Again here, if we roll this paper back a little bit, we see the surface waves show up after the P waves and the S waves, but are also very, very intense. The wavelength from crest to crest of any of those surface waves, any two individual waves, is about the length of the entirety of a P wave. Of the P wave, or rather the first P wave. Within these surface waves, we have a type of wave that essentially does a rolling effect, similar to, well, water waves, essentially. If you look at the upper image here, we see the red arrows show the movement of rocks as the wave, the blue arrow, passes along. Again, think of a crashing water wave. Just instead of water, it's the earth you're standing on, the earth your buildings are constructed on. Or we could talk about a type of wave, as shown below, with a side-to-side motion, right? The second wave of the surface, the second type of surface wave moves the ground from side to side and can be particularly damaging to buildings. You may look at these and think, those look a lot like P and S waves, and, well, you would be right. Waves propagate either with the flow of the wave propagation, either follows or as adjunct to the direction of the wave itself. And surface waves, earthquake waves, water waves, slinky waves all work in the same general format. But as you can tell, since you're literally buckling the earth, buckling the stuff that the buildings and roads are sitting on, you can cause a lot of damage. An interesting part about P waves and S waves in the sense that they travel through the earth is that, well, they travel through the earth, right? This stuff incorporates a bit of Snell's law and things of that nature, but a good way to tell how far a hypocenter is away from any particular seismograph is, as shown here, to use multiple seismographs. So the first seismograph is very close to the hypocenter of the earthquake. Notice all three waves show up in a concentrated time. The second seismograph, however, is still building that surface wave curve, because the surface wave barely got there on time, so it hasn't yet finished out writing the surface wave, whereas seismograph 1 has finished writing the surface wave. Seismograph 3, very far away, is so far away, in fact, that the surface wave and the S wave have not hit it, it only sees the P wave. So, after the fact, you can look at all three of these, and you can kind of use this information, knowing that the P wave really didn't lose a lot of velocity in the course of its travel, though it did lose some intensity if you look close at those charts, at those seismographs. You can use this to correlate where earthquakes actually happen. Very cool science. As I was stating previously, and to review, your focus where the earthquake actually took place inside the Earth in the epicenter, the surface location directly above the focus, or the hypocenter, can be determined using the different velocities of P waves and S waves, and I guess technically surface waves, and a bit of math, a bit of velocities, distance, velocity, and time, and all that stuff. This three-station approach allows you to triangulate what's going on. It's hard for me to explain this in lecture. Doing this in a lab is truly the best approach. Here is an example of 3 seismograms. I'm going to go over how to use these in the following slides to triangulate location, but feel free to come back and look at these seismograms as we go through the example and try to correlate what's going on, what I'm trying to do here. Since I know how long it took for a particular wave to hit me, I can figure out, based on the speed differences of those waves, how far away what happened. I can graph my P wave and S wave curves on a time to distance chart, a time travel graph is said here, and use this information to compile, triangulate, if you will, locations of epicenters and therefore hypocenters. Using this information, back in the day, seismologists would literally pull out compasses, the little 2-footed thing with a pencil on one side and a sharp pokey part the other that you probably used a lot to draw circles in middle school. They would use those and they draw radiuses around, putting the center of the compass on a seismograph station and drawing a radius around based on how long it took the P waves and S waves to reach that location, and then they would connect all those circles together, and wherever all three circles connected, that's where the epicenter of the earthquake happened. As shown here, seismologists back in the day would pull out big old maps, use their compasses, draw circles, and find locations of earthquakes. Here we can see that, where am I at? Paris, the furthest away, the last to get the P and S waves, has the larger circle, and then Darwin a bit closer, and that Indian city, I don't quite know how to pronounce that, even closer still, and all these circles are called great circles. All these circles combine to one location to tell you where the earthquake originated from. In this case, we're looking at northern China, I'm going to call that. This is something that may seem a bit confusing, me saying it in person. When you get down to the lab, you take it step by step, take it slowly, take your time. You will find this process to be not super complicated, given very rudimentary data, and also, I would argue, kind of enjoyable. But, hey, I'm the one that teaches this class, right? So, once you know where an earthquake happened, how do you describe it? How do you describe it? Well, the part we care about, how strong it is, its size. You have two basic descriptors, intensity and magnitude. Intensity is a measure of the degree of earthquake shaking at a given location based on the amount of damage, or how much of the earthquake did I feel. Was the earthquake from my point of view? You also have magnitude, which estimates the amount of energy released at the earthquake epicenter. That is, how strong is the earthquake from the earthquake's point of view. These two sometimes parallel each other very nicely, other times they do not. We'll go over examples. To measure the intensity, or how I felt the earthquake, we use what's known as the modified Mercalli intensity scale. This was developed using California buildings as a standard, but we have an issue wherein this intensity scales the destruction based on you and where you are and what you're feeling. Your response to the earthquake may be different than your neighbors or someone across the world, since it's not measuring based on the earthquake's power release, but how well you felt it. So the further you are away from the earthquake, the less intensity you're going to feel. If you live in an area that it can withstand earthquakes well, it's not going to be as damaging as living someplace where earthquake is more prone to damage from earthquakes. That may seem a bit convoluted. When we go over examples, I think you understand what intensity scale means and why it's not a good way to compare earthquakes to other earthquakes. It's better more so used on the human side of things. As you can see, the modified Mercalli intensity scale goes from 1 to 12, where 1 is essentially you don't feel the earthquake, and 12 is all hell's broken loose, everything's collapsed, total damage to whatever your surroundings are. This really sucks. And as you notice here, there's a lot of words like felt or damage, things like that. Not proper sciencey terms like joules and all these other units. Instead, it's what happened around me. How intense was this earthquake in reference to what was damaged. If an earthquake happened and the table jostled around a little bit and one of the table's legs broke, That's not very intense, right? But if in another country a little bit ways away, someone's house collapsed and it killed their pet guinea pig, that's going to be a lot more intense to them. It would stack up the scale. The same earthquake may have different intensities based on more than just the earthquake itself. Before we go any further, I will remind everyone that I apologize for bad pronunciations. It is not my strong suit. So, seismic intensity. What is it? How does it work? Let's use a case study, the Loma Prieta earthquake of 1989. From this intensity map, we notice that near the epicenter/hypocenter of the earthquake, we have the highest intensity of damage. As it spreads out, intensity decreases. We can notice up by Reno, for example, there are little blobs of 5 intensities surrounded by an overall 2 to 3 intensity. Maybe that's a 4. No, it's probably a 4, actually. We have blobs of 4s, and then we have 2s and 3s poking out in certain directions. Why is that? Does that have to do with the earthquake? Or, more accurate, does that have to do with what is being damaged? If there's a city, something like that, communities that can be damaged by the earthquake, they're going to have higher intensities. Why are we talking about this particular 1989 earthquake in California? Well, because that happened during the World Series. The World Series was shut down because of this earthquake. Very famous event. Anyone out there that knows their baseball even kind of well is familiar with this event. You can watch YouTube and you can see the earthquake happening in real time. Look it up. 89 World Series. You'll see the stadium shake. It's pretty intense. This earthquake happened in California, and California is like one of the wealthiest places in the world. If California was its own country, it'd be like, I think, one of the top 20 countries for terms of wealth. It's ridiculous. But California does have quite a diverse population in it. And as we look at this example here, you have buildings adjacent to each other, one suffering major structural damage, the other maybe had some glasses jingle around. Why did this happen the way it happened? We'll get more into that later. And again, we can look further damage. We have building structures. We have a elevated highway that appears to have collapsed. Not a good thing, right? People could have been on this highway when the earthquake happened, and the highway fell on top of them. Lots of damage can come, and all this plays into the intensity of the earthquake. Not necessarily a description of the earthquake from the earthquake's point of view, a description of the earthquake from the human's point of view, from the structure's point of view, from the financial, from the emotional, the human loss point of view. So we talked about a earthquake in terms of the people. Now let's talk an earthquake in terms of the earthquake, or magnitude scales. The Richter scale, something you've probably heard of before, measures earthquakes based on the amount of energy released. It is based on the amplitude of the largest seismic wave recorded, and accounts for the decrease in wave amplitude with increased distance. The Richter scale is also known as a logarithmic scale. So each step up number-wise in the Richter scale is equivalent to a 10-fold increase in wave amplitude or a 32-fold increase in energy output. So, to determine the Richter magnitude of an earthquake, you first measure the height, or the amplitude, of the largest wave on your seismogram, in this case, 23 millimeters, and plot it on an amplitude scale, shown at the bottom right here. Then you determine the distance to the earthquake using the time interval separating the arrival of the first P and the arrival of the first S wave. In this example, 24 seconds. Plot that on the distance scale to the left. Connect the two dots, and you have your magnitude of your earthquake. This example here clocks at a magnitude 5 earthquake because that 5 crosses the line between the distance and the amplitude. Again, the Richter scale, the magnitude scale, is a logarithmic scale. So if we notice going from a magnitude of 1 to 2 to 3 to 4, we get a ground motion change with an amplitude change of 10 to 100 to 1,000 to 10,000. If you are familiar with your math at all, a log 10 scale is what's going on here. Magnitude 1 has 1 0, magnitude 2 has 2 zeros, magnitude 3 has 3 zeros, and so forth. The actual energy release is given by the equation for Richter scale, which we haven't discussed yet, but it refers to, again, a exponentially growing amount of energy. 32 times, 1,000 times, 32,000 times, 1 million times energy. This keeps jumping up and up and up and up. So a very large magnitude earthquake, let's say 7 or 8, has an immense amount of energy compared to, let's say, a 5 or a 6, even though 5 and 6 are, well, right next to 7 and 8. Aside from Richter scales, we can also talk moment magnitude. This is a measure of the total energy released during an earthquake. You calculate this from the average amount of slip on the fault, the area of the fault surface that slipped, and the strength of the faulted rock. Using these 3 data points, you can figure out the moment magnitude of whatever seismic event happened. Lucky for us, the more strength an earthquake has, the less likely it's going to happen. Here on the far left of this chart, we have magnitude going from 2 to 9, and going from nice, soft, friendly green-yellows to very scary oranges and reds. You'll notice that as the magnitude increases, the per-year amount of earthquake decreases. We have literally millions of magnitude 2 and 3 earthquakes happening every year, where we have 10s or even 1s, 7s, 8s, and 9s. Descriptions here follow. Feel free to pause the video and read these descriptions if you want. A few examples shown here of each of these. Notice there's not a whole lot of 9s, 9.5s. And then energy release in kilograms of explosives. I think they technically use TNT. I don't know why they didn't say that here. But just showing you the stupid amount of energy that comes out of some of these earthquakes. Noteworthy ones you would know. The Japan 2011, I believe that's the earthquake that busted the Fukushima nuclear reactor. Sumatra 2006, that was the earthquake that hit the East Indies islands with a gigantic tsunami killing loads and loads of people. Down there in between 6 and 7, at 6.9, you have the Loma Prieta earthquake in 1989. We talked about that previously, right? That's the one that paused the World Series. So take a few seconds, pause the video, look over this, familiarize yourself. Maybe if any of these are of interest to you, look them up. See what actually happened as all these earthquakes. So we step away from the earthquake as a geologic feature and talk about the human component of the earthquake, namely the damage caused by it. You have, obviously, structures are a common part in human environments, right? How much damage is caused to a building, a structure, a road, etc.? Well, the amount of damage to structures depends on many various things. The building materials, construction codes, the amount of energy the earthquake actually releases, how long the earthquake lasts, the duration of the vibrations, and the nature of the ground beneath the structures. Let's take a case study of the 1964 Good Friday earthquake that happened outside of Alaska. It was a magnitude 9.2, so a ridiculously strong earthquake, and it shaking, the earth actually quaked for about 3 to 4 minutes. We can see from this image 2 adjacent buildings with 2 very different results from the earthquake. One, the steel frame building, doesn't even look like anything happened to it. It just looks like a regular day for that building. The other building collapsed. Why did one collapse and the other not? Well, we can look at this from a building material standpoint. The steel framed building survived. The classic brick and mortar building did not. And we can visualize components as to why this happened the way it happened. Wood and steel, these are flexible materials, less likely to actually break. When we talked about the ruler earlier, right? The ruler will bend before it breaks. If you can continue to bend it but not break it, nothing's going to fall down. Brick, stone, and adobe, by comparison, are very brittle and will crumble and easily fall. So, if you have a building that's mostly built out of brick, it's not very likely to bend and wiggle with the shaking of the earth. It's instead more likely to fall over. Again, the brick and mortar building in that last picture collapsed. The steel frame did not. Reinforced concrete, of course, would be a combination of these 2 ideas, so it fits someplace in the middle of that. We could also talk construction codes, building codes. How well you build the building determines how well the building, and therefore the residents inside the building survive. We have two examples here from 2005 in August and October, adjacent to each other essentially, with very similar magnitude-sized quakes, 7.2, 7.6, one in Sendai, Japan, one in the mountains of Pakistan. The Japanese earthquake, the 7.2, injured 72 and had no deaths. However, a month later in Pakistan, a slightly larger magnitude earthquake had 79,000 deaths and 65,000 injuries, along with 3 million displaced people. That is a ridiculous difference in statistics and damage to and cost of human life. Why is that difference? Well, maybe there's a building construction, how they build the buildings, what's required of the buildings to be erected, that can be attributed to this vast difference. Here we have a couple more examples. This is a total loss of infrastructure from a Haiti earthquake in 2010, a magnitude 7. 316,000 people died during this earthquake. Of course, you can compare this to a Chilean earthquake in 2012, a larger earthquake, an entire magnitude larger earthquake that had only 550 deaths. Why did the response, the death total, the building collapse differ so greatly between the Haiti and the Chilean earthquake? Well, the reason, of course, one of the reasons you could look to is building codes. In Haiti, there were not necessarily any building codes. You can build what you want. So when an earthquake happens in that part of the world, not all the buildings will hold up to the same. Chile has more rigorous, strict building codes. The buildings are more likely to stand. The buildings are more likely to support themselves. And here we have an interesting quote by Hendricks and Turk, whoever those two are. While nature controls an earthquake's occurrence, politics and economics control the outcome. This is because you can construct a building to withstand an earthquake if you put the time and money and resources into the building in order to withstand the earthquake. If you let people build whatever they want, they're not going to know how to build it to be earthquake resistant, earthquake proof. Things that come down, 550 lives versus 316,000 lives. Here we have an example displaying earth materials and the role it plays. Unconsolidated ground can fail. Soft sediments amplify waves more so than solid rock. Even if you get close to the epicenter, if you have your building built on solid bedrock, it's less likely to shake as hard because the waves won't transfer through it as easily, and you're not going to have the same failures. Soft, unconsolidated materials can actually liquefy, turn essentially into a mobile fluid, if you will, which then can cause things to fall. This is a quicksand, if you will, thing would happen. Here we have a graphic, a cartoon of the example of liquefaction, A, B, and C at the bottom. Pause the video, take a close look at that. You understand this process. Here we have some images of some buildings that underwent liquefaction and slumped into the ground. Notice the buildings themselves did not crumble from the earthquake. Rather, the unconsolidated soil, the soft sediment soil that the buildings were built on, liquefied, and the buildings literally sunk into them like mud. This liquefaction process can result in landslides and ground subsidence, which, of course, can cause big issues. If a large portion of the ground slips and moves away, then on top of the earthquake shaking and crumbling things, land is flying at your face. Also tends to not be considered a good thing. And of course, if part of the structure that you built the building on subsides, falls down, your building, of course, falls over. Something you perhaps don't immediately picture when you think earthquake is the resultant damage can thereby create more damage. Fire is a good example of this. Fires can start when you destroy gas and electrical lines during an earthquake. And of course, water lines can also be broken in an earthquake, causing issues with controlling fires. The East Indies Sumatra earthquake is a very vivid modern example of another side effect of earthquakes, that being tsunamis. Notice not tidal waves, tsunamis, destructive water waves that result from the vertical displacement along a fault located on the ocean floor, or large undersea landslide triggered by an earthquake. Here we can look at this graphic down below. The plate subducts, a displacement or megathrust fault occurs at the hypocenter, and the place where the fault touches the ocean floor, the sea floor, actually moves. That fast sudden movement causes the water to ripple up, doing lots of damage. These tsunamis usually happen in the open ocean far away from land and then continue to escalate. An open ocean height differential of a meter can pile up to heights exceeding 30 meters by the time it hits land, moving at incredibly fast speeds. Here we have tsunamis going 340, 800 kilometers per hour, super fast. Earthquake happens. An earthquake happens off your shore and you live on that shore, you need to be worried immediately. The 2011 tsunami that busted up the Fukushima nuclear reactor in Tohoku was a 30-meter high tsunami wave. A Pacific-wide event, this tsunami not only affected Japan but also Hawaii and even the west coast of North America. The entirety of the Pacific Ocean was upturned. Here we can see a picture of the tsunami crashing. Look how huge those waves are compared to that little teeny van in the center of the picture. Just massive amounts of mass moving very fast, not caring what's going to run into. Thankfully, we have a tsunami warning system in the Pacific Ocean that allows scientists to track tsunamis and issue appropriate warnings to affected areas. Seismic observatories will report large quakes to the Tsunami Warning Center, and a series of deep water buoys in the Pacific will detect the energy released by these quakes. Tidal gauges will measure sea level rise and fall, allowing tsunami warnings to be triggered. Here we can see an image of tsunami travel times, or how long it will take a tsunami to hit a particular location, in this case Hawaii. A earthquake happening in South America may take 12 hours to hit Honolulu, but an earthquake happening in the Aleutian Islands in Alaska may only take 4 or 5 hours to hit Honolulu. Not a lot of time for you to prepare, move, deal with the situation. That's why these early warning systems are vitally crucial to not only protecting property, but protecting life. So, we know earthquakes are dangerous, we know earthquakes are deadly. Where do earthquakes happen? 95% of the energy released quakes originate in a few relatively narrow zones that wind around the globe. Major earthquake zones include the Circum-Pacific Belt, the Mediterranean Sea region to the Himalayan complex, and the Oceanic Ridge System. Here we have an image showing these three belts of magnitude and the amount of earthquakes magnitude 5 or greater over the course of a 10-year period. Again, you will notice these things line up with plate tectonic active zones, places where plates are moving, run into each other, causing these breakages in the crust of the earth. We know where earthquakes are likely to occur. We know the huge amount of damage and loss of life they can cause. Can they be predicted? Well, yes and no, not really. We have short-term predictions. The goal of a short-term earthquake prediction is to provide warning of location and magnitude of large quakes within a narrow time frame. Research has concentrated on monitoring possible precursors of major earthquakes, such as changes in ground elevation, rock strain, frequency of groundwater level change, frequency of foreshocks. Given all this information, you can hopefully kind of think about predicting where earthquake is going to occur, but there's no reliable method yet. We can also look at long-range forecasts, the probability of a certain magnitude quake occurring on a, let's say, 30 to 100-year time scale. These are based on the premise that earthquakes are repetitive or cyclical events and use historical records. This is an important idea, not because it's going to tell you when earthquake's going to happen, but it's going to tell you when a strong earthquake is going to happen and helps in the development of uniform building codes and assists in land use planning procedures. Here we have a map of long-range quake hazards in the United States, where gray is very low hazard, running up to red, scary orange and red, very high hazards. Notice along the West coast of the U.S., California, Oregon, Washington, very high chance of earthquake. So you need to build, whenever you build something in those high hazard areas, you need to think an earthquake might happen here. We get a little spot down there south of Illinois, Tennessee, Iowa, no, not Iowa, Arkansas, there we go. Arkansas with a little higher level of earthquake hazard. If you are sitting in class, sitting at your home, and you live up in the UP where we are, notice no earthquake hazard. Around here, we don't build our buildings assuming earthquake's going to come and try and knock them down. We can also utilize ideas such as seismic gaps. If we look at this picture of the Indian-Australian plate hitting the Eurasian plate in Indonesia, we notice that along this megathrust zone, along where these two plates are colliding, we've had lots of very large earthquakes in this span. But there is a location between the 2005 and the 2007 8.6, 8.4 magnitude earthquakes where nothing broke. That means, as this is still thrusting, that area is undergoing tension. That area is soon going to break. And given the earthquakes around it, how strong they are, that's going to be a big earthquake. Earthquakes aren't all death and destruction, however. They can be used to educate us. For example, given earthquakes, we can understand certain things about the Earth's interior. Since seismic waves reflect and refract as they pass through different layers of the Earth, we can look at the path the waves have gone through and have a better understanding of what the waves went through. This studying of seismic waves has given seismologists, geologists, a better understanding of the layer-to-layer composition of the Earth. Its temperature changes, what is made up of way down there, right? We haven't dug a hole 2,900 kilometers deep into the outer core to see what it's made of, but we can make very educated estimations as to the outer cores and inner cores makeup based on seismic wave activity and how things have been traveling through it. As we've talked in previous chapters, the Earth has two different types of crustal layers, continental and oceanic crust. Continental crust is heterogeneous in structure and composition, averages about 40 meters thick, but is thickest at mountain ranges and thinnest at basins, with an average density of about 2.7 grams per cubic centimeter. Oceanic crust forms at mid-ocean ridges, the ocean sits on top of it, averages about 7 kilometers thick, very, very thin compared to continental crust. Composed of basalts and gabbros, again, we talked about that already, and has a slightly thicker average density. Beyond that crust, of course, we have the mantle, which we've talked about extensively in previous chapters, but 82% of the Earth's volume. The mantle is a solid layer with an upper rigid solid, and a asthenosphere that can deform and flow, and then a lower solid. And then finally we can get to the core of the Earth. The outer core we assume is liquid, based on the absence of S waves traveling through the core. Those S waves, those shear waves, cannot travel through liquid, so since they don't travel through where the outer core would sit, we assume the outer core is liquid, with a density of around 9.9 grams per cubic centimeter, and it's mostly composed of, we think, iron and nickel and some lighter elements. Then the inner core itself is very solid, dense sphere with a 13 gram per cubic centimeter density. This information, digging below the few hundred kilometers or so that we've actually dug, is mainly all derived through seismics, and it really tells us a lot of interesting information about the Earth and also the Earth's development and so on and so forth. Thanks for listening to this lecture on Chapter 9 of Geology for Gogebic Community College. Feel free to comment down below any thoughts you have, any questions you have. I'll get to them. Other students can get to them. Have a conversation. Enjoy. See you in the next chapter.